Okay, sorry. So welcome everybody. Thank you for joining us for this for the fifth talk of this seminar. Today's talk will be about fibrations, and the speaker will be Alex. Alex, take it away.
Okay, so the goal is to explain the result, which is quite technical. So I will only state it, which says that right fibrations of infinity categories can be classified by functors from S opposite to infinity groupoids. But most of the talk I will be talking about the case for ordinary categories, which says that there is an equivalence between fibrations on a category and functors from the opposite of this category to groupoids. So from this side to this side, it is a Grothendieck construction. And then, so that's what I will explain first. And then from this side to this side. And then I will explain right fibrations. I think we already saw some fibrations last week. And then define the opposite infinity category. And at the end, I will talk about this. Okay, so if we have a functor from a category D to the category of groupoids, then we can define another category, C, as follows. The objects of C are pairs D phi, where D is an object of the category D, and phi is an object of the groupoid G of D. And the arrows well, an arrow from phi to D prime phi prime is a pair F alpha such that F is an arrow from D to D prime. Then if F is an arrow from D to D prime, then G of F is an arrow from G of D. It's a functor from G of D to G of D prime. So in particular, it takes phi to G of F of phi. Then alpha is an arrow from G of F of phi to phi prime. Okay, now clearly we have a forgetful functor from C to D. We just forget the second component. So now we want the opposite construction. Which we can only do when the map F, when the functor F is a fibration. So we say that F is a Grothendieck fibration over groupoids. So I will just say fibration to refer to this kind of fibration. If the following two conditions are satisfied. So the first one is that for every object of C and every arrow in the category D from an object D to F of C, then we can lift the arrow F, so we can find an object and the second condition is that for every pair of arrows in C, then we can lift, well, we can find a filler for this. So if there exists a filler here, then we can already find it above. Sorry. So with this, we can define a functor. So given F fibration, we can construct a functor from the up to groupoids as follows. So objects map to the fibers so by this I mean these fibers, and then this condition 2 implies that this is in fact a groupoid. And then for an arrow from D to D prime, then we have to find an arrow from CD prime, a functor from CD prime to CD, which is given by this listing. So we can lift this, and then using the property 1, we can find so the map, well, the map takes C prime to C. So this is only defined up to isomorphism, and so to do it precisely, we should work with 2 categories. I won't do it here. If instead of groupoids we consider sets, then we would have instead with similar constructions this equivalent. So discrete fibrations over D are the same as functors from the op to set. Okay, so now for infinity categories, we need right fibrations. Since I think last day we already talked about fibrations, I already have written it. So in terms of lifting property, if we can lift all the horns of the map of this morpheme of simplicial sets, then F is a can fibration if we can lift all the horns, but the bottom one is a right fibration. If we can lift all the horns except the top one, then it's left fibration, and then if we can lift all the inner horns, then it's an inner fibration. And if S is just the point, then can is the same as left and right fibration, and then X, and the same as saying that X is a can complex, and inner fibration is the same as X being an infinity category. Now, I won't explicitly use infinity categories, but since they appear in the expression that I wrote and we have not defined it yet, I do it. So the opposite of a simplicial set, it's just, well, if we have a simplicial set X, then the opposite is just the simplicial set with the following phase maps. So we reflect all the phase maps, so we have this. So if C was just one category, with C1 the set of objects, the set of arrows, sorry, and C0 the set of objects. Then the 0 of an arrow return C prime, and the one of an arrow return C. So the opposite is just what we have done right now with the simplicial set, which is well, the 0 is the 1, and the 1 is the 0. So we just change the direction of the arrow. Okay, so in particular, right fibrations are dual to left fibration. And if X is an infinity category, then the opposite is also an infinity category.
And one question.
Yes.
In what sense are these two fibrations dual to each other? Or maybe you didn't want to discuss this?
So if so I mean that if this is a
What do you mean by the op operation?
yes.
Sorry. Okay. Okay, thank you.
Okay, so one moment. So the result in the context of infinity categories is the following. So in Lurie's book is the one. But it is only partial. If P is a right vibration, well, P is a right vibration, even on leaf, there is a functor from S up to infinity groupoids that classifies P. Okay, and one remark. That P is classified by F if and only if for every vertex of S, then this fiber is essentially small. So to see this, so this is technical and we will need model categories and simplicial categories, but I will just say state this other proposition which says that the nerve of a vibration if F is a vibration, then between categories, sorry, then its nerve is a right vibration and so the idea is the following. So if it is a right vibration, then all the top horns can be filled. So because these are categories, it is already an inner vibration. So this lifting property, which it satisfies because it is a right vibration, it is equivalent to one of the definition of vibrations. And this one is the same as the following. So it says precisely that if we have a diagram like this, then we can fill this. So this is the same as the condition 2 of the definition of vibration, but only the existence. Well, filling this horn is uniqueness. Well, and the rest is automatic. So I think I've been very quick because that's all.
towards the end. Sorry, Alex, you finished?
Yes, yes.
Okay, so thank you, Alex. Yeah, are there any questions?
Can I ask?
Yes, please.
Alex,
Yes.
you introduced three or four kinds of vibrations in simplicial sets. Three of them. No, what's the number? Left and right vibrations are classified by functors into groupoids.
Yes.
And what about inner vibrations? Do they classify something?
I'm not sure. So left vibrations by dual properties, they are classified by functors from S to infinity groupoids. I think you are not. Are you seeing how I move the paper?
No, we cannot.
Yeah.
Okay. Well, so in any case, I'm not sure if inner vibrations are classified or by what are classified inner vibrations. So left vibrations are classified by functors from S to infinity groupoids by duality.
Yeah.
And so another kind of vibrations, which are Cartesian vibrations, are classified by functors from S up to infinity categories.
Yeah, those are the generalization of Cartesian theories that classify functions into categories. No?
Yes. Yes.
Yeah. Okay. Thank you, Alex.
Any further questions? Okay, if not, let's thank Alex again. Thank you, Alex.